So I'm going to do a video on anti-gravity physics. In this video, I'm going to show you everything that you need to do in order to create your own anti-gravity physics game. The tools I'm going to show you will effectively work whether you're using Godot or Unreal or largely even writing your own, except we will be depending on certain parts of Unity physics, such as RigidBody and physics raycasting. Most of this will be mathematically simple. It's not going to be that complicated to learn. As long as you have a basic idea of how to move an object using a vector 3 and its position, then you're fine. The items above me are effectively what we're going to be covering during this. Not necessarily in this order, and some areas will have a lot less focus. One thing I want to point you out to is closer towards the end with the muscle and exotic car physics, because I don't want this just to be how do you make a car hover and switch to which wall. I want to show you how to think about physics. How do you want the game to feel to the player? What's exciting about that to you? So the first step for the anti-gravity physics is simply to make an object float. To do that, let's start by creating some grounds. 3D object, quad, and I'm going to press F to focus in on here. I'll call it ground for now. One quick tip that's in here, if you look at over here, we see the axes that are inside the world. And so the red axis is the x-axis. It says x there, z there, y over there. So when I see red over here, that tells me that the x-axis will cause this to rotate around the x-axis so I can flip it up using the x-axis. So let's go to x and try 90. Perfect. Otherwise it would have been negative 90. Now let's increase the scale. We're going to go by 1,000 to 1,000 to 1,000. Now I need a cube, some kind of block that's going to act as a car. So let's create an empty object for the car. Create empty car. And inside of it, we're going to create a cube. So where is this one? Create 3D object, cube. And now we're going to set its values inside of here. So its scale, let's go for a scale of, say, 3x, a y of 1.5 compared to 5 meters long. To me, that's about the size of a car. Now, it's very close to the camera, so let's move it farther away. Right here seems good. Let's give it some different color to stand out. I'm going to go into my game folder, right-click, create a folder called Materials, and then right-click and create a material called Car. I'll drag Car onto there and set its color to red. Now, let's add a component, RigidBody. Now, let's create our script for it. So inside of this, I'm going to create a folder, scripts, and the first script I'm going to create is called skateboard. Create script skateboard. So if you're not familiar with the term skateboard, in electric vehicles, at least when they were first coming out, there was the concept that the skateboard was the bottom of the car. It contained everything that was necessary for it. So now we have our skateboard script. Our skateboard is going to need to detect a distance, how far we are from the surface of the ground. So we'll use a transform for that, but we do need to know what that distance is. So I'm going to say public float max distance, and let's go with equals 5 for now. So about 5 meters up is that target range where it's no longer going to be applying any more force to it. Now, the gravity is going to be forcing everything down. I need to apply a counter force, and I need to know how much that force should be. Now, that number will change depending on what I'm doing with this, but for right now, I'm taking all of the gravity and fighting back with just 1 point. So in this case, we do need a force, public float max force equals, and this one, let's just say it's 1,000. The last thing we need is the rigid body. Public rigid body, RB, we're just going to set it. When we're manipulating physics, we want to do that in the fixed update. So public void fixed update. Var distance from ground equals, and that's just going to be transform.position.y. Now we need to figure out how much power we're going to apply to it. The objective is that as that car gets closer and closer to the surface, there should be more and more pressure fighting between the two, trying to push it back up. But if it's all the way outside of the range, like it hits that 6 meter, it should be applying no more pressure. Power equals distance from ground divided by max distance. That gives us a percentage between 0 and 1 based on how far away we are. So if we are all the way at 6 meters, it's going to give us a value of 1, a power of 1. But that's the problem. We want it the other way around. It's actually the inverse power. So in this case, this one's going to be inverse power. And our real power, var power, equals 1F minus inverse power. I like explaining it out this way because you get to see the entire reasoning behind the math. And now let's go var power equals 1F minus, and inside of here, we're going to say transform.position.y divided by max distance. So we just shrunk these three lines into one line. But if you've never faced it, this makes it easier to understand. So now we have the amount of power we need to apply to the object. That's going to be this.rb.add force. And now it wants to know how much force to apply. This is linear force. It's just going to apply the force evenly across the entire object. So if you tell it you're pushing a force up, the object is just going to move up. No rotations or anything are going to be part of this area. So that's power times, and in this one, we need time.delta time. The reason we need time.delta time is because this number up here is effectively how much force we're exerting per second. But we're going to divide that up by how many times we actually get a chance to exert that force. Now we need to multiply that by vector 3 dot up. So gravity is making it go down. Our anti-gravity force is pushing it back up. Do I have this in reverse order? Distance from ground, max distance. It should be the larger number divided by the smaller number. I have this in reverse order. Control X divided by the smaller number. But we've never actually included the force. We have this max force variable hanging out here doing nothing. It doesn't matter what we set it to. So let's use it. Max force. So we need the max force times the power reduced by multiplying it by delta time against the vector 3 up. Returning to unity. Okay, that pushed up and now it's bouncing all over the place. Let's fix the bouncing. Let's put in linear damping. There we go. Now, if I move this up and drop it, you can see it found its equilibrium pretty quickly. If I drop it down here and let it go, it pushes its way back up. That is 2.29. I'm just going to set that to 2.25 or 2.5. Let's make it move. I'll go back into skateboard. I'm going to need to know our move information. So that's going to be input action reference, public input action reference, move action. Next, we're going to need to know how much move force, how much forward force or drive force. So let's call this one public float drive force equals also 1,000, I guess. And public float drive torque. Torque is going to be our ability to turn, QUE, equals, and in this one, I'll put it at about 500. Max force up here and drive force, that gets a little confusing. So we're going to call this the maximum thrust force. Now we need to start reacting to move action. Private vector 2, and this is going to be underscore move control, move input. Now let's put in our update code. Public void update. And inside of here, I need this dot underscore move input equals move action dot read value. And we're going to ask it for the vector 2. Now we need to apply that move input. And I'm going to do that down here. This dot RB dot add force drive force times underscore move input dot Y. That's up and down, forward, backwards, as we're going to think of it, times, and now we need time.delta time. And finally, we needed to tell it to go forward. But if we're turning it, we need to make sure it's its localized understanding of forward. So that is transform times transform dot forward. Now, keep in mind, sometimes we're going to be pressing down, so Y will actually be a negative number, which makes us go back. So this handles forward and backwards. Let's also shrink this down a bit, so it's easier to follow along. This dot RB, we need to know how much torque to apply. Dot add torque. We need the drive torque. So that's drive torque times underscore move dot input, move input dot X. So we're going to use the left right value times time dot delta time times. And in this case, we need to know how it's going to turn, which shouldn't be the up value because maybe we're tilted on the wall. And if we try to turn it, it's actually going to make the car flip over. We're going to need to get the transform up. Transform dot up. That should be it. Let's also put this into multi-line. Now inside of here, it does want the move action for the input. So I'm going to click on this one, click on the little arrow here and get it to drop down with a list of what we have. Now with the default URP package, it doesn't include input system actions. And inside of there, it has one for player move that's already tied into the gamepad arrow keys. And now let's press forward. That did it. And back, same. Now let's press left. Excellent. And right. Okay, now I let go of right after it started doing that, and you can see a problem here. It just keeps spinning. Well, that's no good. I'm going to fix this right now. So we're going to raise this one as well to 2.5. Let's see how that feels. So when I turn this, I can drive it and I can move it around and I'm letting go. So it's a little slower, but it'll let us see and debug what's going on. We're going to create a simple script that lets us follow it based on just a little bit of time offset. On the car, I'm going to create a child object, create empty, and I'm going to call this camera anchor. While it's selected, I'm going to hit Control-Shift-F. That aligns it to my exact coordinate and the exact rotation, looking down directly over at the object. Let's go create script, and we're going to call it camera follow. I want to put an error in here on purpose. Even though I've developed this like 40 or 50 times now, I still make the same mistakes. And then it throws me off and I spend time trying to figure out what's going wrong with it. We're just going to do public transform camera anchor target. We need a few pieces of information, like how quickly we're going to catch up. Public float catch up pressure equals 3. So basically, that's going to be about 1/3 of a second. We're going to do this in the update function. So public void update. This.camera anchor target dot position equals, and this is going to be vector3.lerp, this.camera dot position. No, sorry. This is where we are. That's what we want. So that is transform dot position. And it's not the anchor position, it's transform. We're on the camera and we're going to tell the camera to go move over to the target position. The second position is the camera anchor target position. And the last thing is the time that we're going to put into it, and the catch-up pressure. Now remember, this is a value that should typically be between 0 and 1. This dot catch-up pressure. We're going to multiply it times time.delta time. We need to do the same thing with quaternion. It's so close, I'm just going to grab these variables, Control-C, and paste it. Okay, now this one is going to be rotation, and that's going to be quaternion.lerp. Again, it's going to want rotation, and it's catch-up pressure times time.delta time. This should work, but I'm also expecting it to be a little choppy. I'm going to put the camera over here. Let's take our camera, Control-Shift-F. Good. Our camera's aligned over here because the first thing that'll happen is it's going to move right behind the car, but it'll do that gradual slide over in a short period of time. So down at the bottom of this, I'm going to add component, and that's going to be camera follow. All right, camera follow is in here, and now it wants to know the camera anchor transform, which is over here, camera anchor. Drag it in and play. Okay, so I'm now following behind this, and as I run it, it's moving over. Look at, do you see that shaking that's happening? That's a horrendous jitter experience. That is literally because we are doing this in the update instead of the fixed update. In the camera follow script, we're going to change it from update to fixed update. All right, let's try driving and turning. There's no jitter anymore. The jitter helped kind of show that we actually were moving a little bit better, but that is a much smoother operation overall. Now, before we go any farther, I want to start resetting the world a little bit so that we have some obstacles to work with. I want some steps and I want some kind of a slightly curved wall. So to begin with, I'll add some cubes. Over here, right click, 3D object, cube. R to stretch it. Let's just go out this way, a little farther, and a little bit wider, and maybe a little higher up. Great. W to move it. Let's call it block for now. Let's create a material for the block. So create material block. We've got the material. Let's set its color to maybe right there, bluish green. Sure. And now let's drag this block over to the block. Excellent. There, I now have a curved space that I can ride around in. Let's try this out just to see how it's going to work. So here's the car, and as I drive forward, it stays the same height. It doesn't raise with the stairs. In fact, it gets blocked by the stairs. We need to start getting it to determine how far it is from any surface it drives over. And we're going to do that with a raycast. So let's go back into the car code, the skateboard code. And inside of here right now, we're determining our power based off of transform position.y. I'm going to get rid of this original code up here. We're going to obtain a different value for this. First, we're going to need a hit, which will be raycast without the caps lock. Raycast hit equals new hit. Actually, no, we're using out, so I don't need to. All right, now we're going to do a test for how far and in a particular direction. So we'll need a PhysX raycast, PhysX.raycast, and it has several options. We can start with the origin. Where is this going to be? Well, that's pretty straightforward. Transform.position. Next, it wants to know what is the direction. Vector3.down. Okay. Next, it's going to want to know max distance. That's it right there. Max distance. And then finally, I want out hit. And it doesn't like something about what I just entered. So let's find out why and what that is. I'm going to take away out hit, Control X. And then on this one, Control V, comma. There we go. It was out of order. All right. So the origin is our car, the center of our car, basically. The direction is going to be down, and it will output a hit. Now, this is also returning a Boolean value. So I'm just going to say if we get a raycast hit, we'll still need to be able to add force and torque. So we can drive, we can turn, we can move. Instead of transform position.y to give us that distance, we're going to use hit.distance. There we go. Let's test this out. All right. So it's not working. Something is definitely wrong. Let's go find out what. Let's now take a look at where we are starting from inside of this. We're very low to the ground initially. However, this is the center point. No. Pivot. I want the pivot. Oh, look at that. The car's pivot is actually way down here. This is the transform position that's being returned. So what I'm going to do is go take the cube and I'm going to realign this one to 0, 0, 0. I put it on the same object. Now I'm going to take the car and let's drag the car back up. This must have happened from some point where I clicked the cube and moved it. But anyway, so we want the car to be up here. Now, I should also reset where that camera sits. What is going on with my camera right now? For some reason, the editor camera got off alignment, and now I closed the scene and put it back, and now it just reappeared in the correct alignment. I've never seen the Unity editor do that before. Now I'm going to reset the camera anchor. Control-Shift-F. Now the cube should be right there. That should be the pivot position. So this is the center of car, and it's also in the center of cube. Perfect. Okay, so now for the real reason that we were actually trying this, we were using a raycast to get our distance. Let's test it out. With a raycast, we should be able to go up to the stairs and have it push up, which it does. And then when we get to the end, it should drop back down closer to the ground. Also, which it does. What we've effectively done here is we've created a thruster back into skateboard. And inside of here, I need to create a class that's going to hold all the information for the thruster. Not a class, a struct. When we're dealing with arrays of objects, we don't want classes. We want to use structs, especially when it's small amounts of data and we'll be using it all in sequence. Public struct thruster. I'm going to add additional fields to this so that we can actually debug the data. That's going to be incredibly important because it's going to be really hard to see what's going on with the physics. And so we're going to want to display visual lines, debug information, text that's going to show up inside of the editor. The first thing we're going to need is the local position and the local normal. Public vector3 local position. Public vector3 local normal. Now, to make sure that all of our math is done correctly, we want to render the normals that we get out of this. Public vector 3 world position and public vector 3 world normal. Now, to be able to make the thruster work, we're also going to need to know how much power it has. So public float power. We're going to use the power and multiply our max thrust force by the power. We're also going to want to know what distance it thinks the ground is. So public float distance to surface. The next thing we're going to want is an array holding on to this information. Private thruster thrusters. We're going to leave it blank for right now. We're going to use the start function to initialize this information. One more piece of information that we're going to add up. Public vector 2. No, we'll use vector 3. We're only using 2 of the fields in it for now, but we could use all 3. Vector 3 offset. I'm going to call this engine offset. So the concept of engine offset is to say from the center of the vehicle, how far do you move along the z-axis, moving forward or backward, and how far do you move along the x-axis, side to side, to get to the corners. In the start function, we need to start using this. We're only going to have one value going into this. Var t equals new thruster. And now I need to set the thruster's local position. The local position is 0. It is the center of the object. I don't need to set a thing here. However, I do need to set the normal. Local normal equals vector 3 dot down. Next, I need to actually generate the array of thrusters. Thrusters equals new. And inside of here, I'm going to pass in t. Inside of fixed update, we need to start looping through that array for int I to thrusters dot length. You get rid of the end and put this down here. I'm going to close it up over here where we're doing the raycast physics and operating against the physics for that object. We're going to need to convert from local space into the world, from the local direction into the world direction. Var t equals thrusters I. We're going to say t dot world normal equals transform dot transform direction. Transform direction t dot local normal. Now we're going to do the same thing for the position. T dot world position equals transform dot transform point t dot local position. We have now established what the world position and direction is supposed to be, but we're not using the t value. So let's start using this. Our origin will now be this, t.world position. And our direction is going to be t.world normal. As long as we actually had a collision, we're going to say t.power equals, and let's gather this piece of information too. We now control the power. Excellent, that's stored. We're also storing hit distance from the raycast hit. So instead of using this one, we're going to say t.distance to surface equals hit.distance. Now I'm going to use this value to pass inside of here. Outside of the if statement, I'm going to say thrusters I equals t. We're putting that thruster back into memory. Now, I also want to deal with the else condition. So the else condition means that we didn't come in contact with anything. But in that case, we still have these 2 values. They're going to be whatever they were the time before. T dot distance to surface, and this one's going to be max distance. That was the maximum distance the raycast goes. So that's all we're going to measure it out. And we're also going to set the power. T dot power equals 0. If we are at the maximum distance or greater, then we have a power of 0. Now, this physics information isn't going to help us unless we can see it. So I'm going to go up here and let's grab the for loops that's inside of the fixed update. All right, so I now need another function. We're going to use gizmos. Public void on gizmos, and this is on draw gizmos selected. On draw gizmos selected will run in the editor, which means it's going to start executing this before a start function has even run. So I'm going to do a check on here. If thrusters equals null, return. So we've got this thruster. I want to draw the lines. The starting point is easy. That's thruster dot world origin or world position. But we're going to need to know the end point. Vector 3 end point equals, and this one is going to be t dot world position plus t dot world normal times t dot distance to surface. That effectively gives us a line to go the exact same amount that we were checking with the raycast. Let's set the color. So we're going to say gizmos dot color equals, and I want something that should stand out. Let's go with maybe a red or violet red. Now we're going to say gizmos dot draw line and it needs to know where it's coming from and where it's ending. Well, we're going to say t dot world position, comma, endpoint. Draws a line from one point to the other. Now we're also going to draw the text, handles dot label, and inside of here we're going to give it the position, which is going to be that endpoint again, comma, and now we're going to give it the text. Inside of there, I'm going to give it a little bit of formatting in this. I'm going to say this is for power, plus t.power.toString, and inside of here we'll say 0.00, formatted to 2 decimal places out. But that's not the end of this one, so I'm going to hit enter, tab plus, new line, and this next one is going to be, close out that previous one. I'm going to put the p colon right before there. Control X, put it right here. Okay, perfect. This next one is going to be distant colon plus, and this one's going to be t dot distance to surface dot toString 0.00 plus, and just close that out. This gives us debug information anytime we have the car selected. Let's check it out. We should get one line from the center moving down. Now, we won't get this immediately. We have to run the game. There we go. We are currently a distance of 2.55. Our max distance is 5. So we are really close to a power of 50%, which is exactly what we should be. You can see if I move it up, the distance increases, the power goes down. So now if we want to get tilt to start operating in our car, we're going to need to have at least 4 points. Let's think of it as a car where the wheels are going to be in contact. In fact, when you're thinking about car physics, this is car physics. The only thing is it would be closer to the ground. However, we're dealing with hover physics. It's basically the same thing, but you don't put wheels in. There is one thing that I think I put in the last time, offset, engine offset. We didn't use this. I got ahead of myself, but we're going to use it right now. So let's go into the code and we're going to put in an engine on each corner. Right now, we're creating only one thruster. Let's create 4. I do want to have an array of polarities, but we're going to create one for X and Z to basically describe, are we on the left side or the right side of the car? Are we on the front side or the back side of the car? So vector3 polarity equals new. And inside of here, I'm going to put new vector3, and this will be 1, 1, 1, 1. There we go. We do need to make the X and Z alternate from left to right, from front to back. So I'm going to put in minus, minus over here, and then I'll put in minus and minus over here. Now we need to loop through each one of the polarities. So 4, and to upper is going to be 4. We actually know how many thrusters we're going to generate at the beginning, so why don't we just do that? Control C, and let's go up to here, equals new thruster 4. Now let's do this, Control X and Control V. I didn't need that code. However, it'll be pretty close. So I'll just say this one, I equals T. In this case, we're still setting the local to down. We're just creating 4 of them. They're going to be placed in the different corners, but the positions need to be changed. So I'm going to say T dot local position equals engine offset times T dot polarity. I want the polarity, but I can't do that. That one's not supported in here. I'm sure that there's some known named function for this, but I'm just going to create my own. So over here, public static vector3 mul for multiply, vector3a and a vector3b. Now the values are just going to be return new vector3, a.x times b.x, a.y times b.y, comma, and a.z times b.z. So yeah, we're just multiplying each one of these to get our x, y, and z value across. So I can't use this one. I'm going to use mul. For all I know, there's a function that already exists for it. If someone knows that, that'd be awesome. Please share it out in the comments for all of our sake. So now we have 4 thrusters in here. All I had to do was change the initialization, where it starts, and the rest of the code should automatically be able to deal with all the different thrusters, and it should be able to give me debug information for every single one of them. Okay, we've still got only one line showing up. Let's figure out why. And actually, I suddenly realized, I think I know exactly why that's happening. Yes, all offsets are 0. Okay, so the engine offset, let's see, how far out to the side do we go? And basically, we're going to be looking at the scale of the cube that we put in here. So that's 3, so we'd be putting about 1.5 going across, and 5 this way, so 2.5 on the other one. And that should put us in the corners. Let's stop, go to the root car, and we're going to put 1.5, 2.5, play. So I guess we did have 4 points. They were all just right in the center. There we go. I see 4 lines there. Let's go over to, what do I even have that one up? Close tab. All right, so inside of this one, you can see we've got a lot of extra information there. Every single one of it shows that we are 0.12% power, or 12% power. And we are at a distance of 4.39 meters. All right, now, will this tilt? No, it won't. But let's try it. Let's see what happens when we drive. I drive, and the car still pushes up. Why does it just push up instead of do this unevenly? And that is in our physics function. Every time that we find a collision with the ground, we are adding a force. Now that force is balanced. It's balanced across the whole object. It's direct linear correlation. So you tell it to move left, then it's just going to move left. Instead of add force, we're going to add force at position. This is the force that we're adding. And now wants to know the position that that's going to happen. That's t.world position. Now we should actually get a wobbly car. There we go. Look at that. Hits the ground over there. And there we go. We've got our wobbly car. It can drive around. Like, we still want to tune these numbers. In this case, I consider these numbers fairly slow. And also, let me turn gizmos on. The car's not selected. That helps. And now at this point, I can just drag the object around. And I can see how it interacts with different surfaces. So for this next part, I want to bring the style of the car up. I also want to show you a couple problems I'm going to run into when I try exchanging out a model. So let's dive into this. The first thing is I'm going to be using this one from UnityFan. Now, you'll notice in the title, it says free AI. It's AI-based concept car. Now, when they say it's AI-based, what they mean is that they used an AI image and then they went into Blender and manually generated the entire model. So in that case, if you have qualms with AI, I would hope it doesn't necessarily jump to this one. Anyway, because this is public domain and it was manually created by a human. For that one, I already happen to have the model in here. Let me bring it up on my side and let me bring up Unity. Create a models folder. And I will drag in the FBX version. Now I'm going to drag the futuristic car over into car. Okay, we can see its initial position and information is off. So let's change that. 0, 0, 0. That aligns it with this object. Now, one thing about this is if I go to the cube and I disable it, you can actually see it's like right, the cube, our surface spot, our center of the object was literally in the center. This one is at the bottom. So that's going to be an issue. It also comes with some extra stuff that we don't need. So I'm going to expand this out. Let's take this object, prefab, unpack. I'm going to select this and delete it. Where's the rest of it? I'll get rid of that. We're going to keep the cube enabled, but I'm going to turn off the mesh renderer or get rid of it. Now we can see that the physics collider no longer lines up with it. And we can also see the car is a little shorter and a little thinner than what we were using originally. So we're going to alter some of our setup of this. Let's go to a top view. There. And now perspective, or not perspective, isometric. Let's go to the collider, edit it. And let's go to the side view. And let's edit this one as well. Now we're going to run into a balance issue with this one because we just manually adjusted this. And so let's see about getting that taken care of. For now, we've got this one set up as the visual. Let's try it out. I'm expecting it to be tilted to one side and we're going to see it start to drift. No, it's fine. Okay. We were really lucky. Let me try altering this slightly. If I were to take the cube, go to the editor, and I will manually throw this off. It should be tilted a little bit. Let's click the object. Yeah, this is tilted a little bit, which right now, I guess we're still lucky enough that it's not throwing it off, but you can see that the power on this side is 13 and the power on that side is 12. If we were to stay here for a while, we would see a very subtle drift where it starts pushing it backwards. This is actually suggesting a different problem in my math right now. So far when we've been doing this, we've been working against a stable gravity where gravity is always down and our car is always pushing back up. So the idea of it getting pushed off to the side was never a thing. Let's find out where we are getting our values. We transform the direction. Yes, we are checking that in that direction. And now when we apply the force, add force, look at that. we're still going vector 3 dot up. The T world normal, Control C. However, the T world normal, that is the direction down. So, but this one we have vector 3 dot up. So we need to get the opposite of it, which is pretty easy. It's minus T world normal. Now let's try this out, and I'm expecting it to shift backward or shift forward. But you can see it actually is moving now. This gap between here and here is getting smaller and smaller until eventually it will overlap it completely. Additionally, if I grab the object and I place it on this, it starts pushing its way back. So there's a couple ways that we can fix this, because we manually edit this, or it could also be that the model that we get in, and if we're using something more complicated for our physics than a cuboid, then we're not going to be able to set the center of our mass very easily. What's happening in here is that the rigid body is looking at the mesh and it's mathematically trying to pinpoint that center of weight. But let's fix it for now. All I'm going to do is I'm going to turn off the automatic center of gravity. We're just setting the center of mass to 0, 12, 12. Even though these before it was 13 in the front, 12 in the back. We're going to need more than just 4 thrusters. I found that 28 tends to feel about the right area. Instead of going to 28, I'm going to push this out to a configuration of 12. All we're going to need to do to change this is go into our start, because our start establishes everything about how many of these we actually have. So let's say thrusters, we're going to have 12 in here now. I'm still going to keep this as 4, but I'm going to use a new setup of this because it's for each engine. Every engine is going to have 3 thrusters on it. So one pointing down, one pointing either forward or backward, depending on the side of the car, and one pointing left or right, again, depending on the side of the car. All right, so I need to get the modified index, and that's going to be int mi equals I times 3. Okay, so I is still going to deal with our polarity. So that's going to be the index that we're pulling from there. And mi is going to be the index that we pass into here. So I'm going to put this down there. And now we're going to pass in mi. Okay, so we have this thruster. We're setting the down position. This works. We'll keep the same down position. Now, since we're going to be using polarity multiple times, I'm going to create a variable out of this. So let's just go Control C and P, and I'm going to get the polarities. Var P equals polarity I. So now I've got the local position, and I'm multiplying the engine offset by P. That way we've got the polarity, but we'll be able to reuse the polarity again. So let's create our forward thruster. So we're going to say T equals new thruster. All right, one change that I do want to make here is that we are immediately setting the local position based on multiplying the engine offset by P. And why do we want to keep reconstructing this for every one of these thrusters? All 3 of these thrusters are going to have the same origin point. So in order to do that, I'm going to create another variable here, Control X, and we're going to call it var origin. So the origin equals that. And now we're going to say our local position equals origin. Now our new thruster is going to be able to use this as well. T dot local position equals origin. Now we need the normal. So the T dot local normal, well, we're going to create this as a new vector 3. And we'll just know that this is going to be the forward or backward vector. So we'll say that this one is the backward vector or forward vector. That one's going to be 0, 0. And then we're going to be using polarity dot z. Thrusters plus mi equals t. Well, now let's duplicate this code because we've only got one minor change to make. If we want the one to go side to side, we're going to put that over here. That's p.x. And this one is now going to be 0. So we've effectively created a normal because our boundaries over here, our polarities, are set by 1s or -1s. That should give us all of our thrusters. Let's check this out and see if we have 12 thrusters sticking out of our vehicle now. I see 12 thrusters. All right, so let me go over to the scene view. Look at that. There we go. So now that means if I drift close to this wall, I should be able to come back. It should push me back. Let's go try it. There we go. I'm just pushing right up against the wall, driving straight into it. I'm only pressing forward here. So now I'm over here, and let's increase the speed a bit. Drive force times 2. And in this one, I'll just drive forward. I'm only pressing forward. Those are pushing me away. Hey, I'm even driving sideways right now. Now we're going to get into something that I call conditioning, and that's basically where we take the physics, and rather than letting each thruster react in a consistent way, we're going to alter the flow of that physics. So, for instance, we want the car to rise as it hits the edge. So if I were to play this game right now, and let's say we were just to go drive into a wall. I turn over, and then I run towards the wall. That's it. It just drives towards the wall and the wall pushes back. That's not very fun. Not for a hover race. I want to be able to drive up the wall. And right now I can't. How do we fix this? Well, the conditioning option is basically where we say, let me go over to scene. And we say, hey, we have some force on the front. We don't right now because, well, actually I just do this. Let's drag that forward there and then let go 1 frame there. So we have some force on the front, and that's pushing it backwards away. Now, what if we were to take that frontal force and shift some of it to the bottom? If we did that, if we took force from this side, power from this side, and exerted it towards the bottom, then the car would start pushing up as well as back. Here's the wall. Here's the car coming up to it. And now it gets up to this, and here's that point where the physics can start to cross over and it pushes back. But instead, as it gets up to here, it's going to try pushing from the bottom and starting to tilt it. So the front half of the car is going to start rising. And then as we get into there, the car starts rising until eventually it can just drive up the surface. There's effectively 2 values that I'm going to want to store for this one. And it's X to Y and Z to Y. So public float X to Y, public float Z to what? Z to 1. And so this is a percentage of how much we want to transfer over to Y. We've got only 1 loop here right now. We're going to change this into 3 loops. Okay, so the first loop is supposed to be all about detection. We want to detect what's going on in the world around us. The second loop is where we're going to do our conditioning. And then the third loop is where we're going to apply the physics that conditioning or that power set up. I'm going to copy this loop. I'm just going to take the whole loop, Control C, and let's put it down here just after it. And I'll just get rid of stuff that I don't need. I suppose at the top one, I'll put a little comment above here and say this one is for detect, measure. So the first part, we need to detect our information. The only part we're not going to have in here is the actual application of the force. Otherwise, we are absolutely setting what our power and distance is and putting that back into thruster value. In the conditioning, we're not going to do any of those. So let's get rid of this information. So this is going to need more stuff put into the conditioning. Measure, condition, and the last one is going to be apply force. Now in the apply force, we do need to get the thruster, but we don't need any of the physics hit stuff. So I'm getting rid of that. We don't need to set the value. This dot RigidBody dot add force at position max thrust force times T dot power times time dot delta time times, and now I need the T dot world normal. Okay, that should be the force that we're applying. Next, I need to put in the position, which is T dot world position. Oh, the T dot world normal. That's the direction the thruster or the raycast is pointing. We need the opposite for that force back. So in this case, it's negative times negative world normal. Play. All right, we're still floating. I can drive forward a bit, and let's see how this wall handles. it pushes me back, just like we were expecting before. So our thrust code works, our measurement system works. But now over here in the conditioning circuit, I need to start transferring the information. The conditioning circuit is different. In the other ones, the information it needs to know is available in that thruster. We need to know one thruster's information compared to another. So this loop is actually going to be closer to this information down here. We need to know that we have a forward vector, we have our back vector, and we also need to have this equation in to effectively get what index we need. So what I'm going to do is actually copy what we have in our start code for our loop. So in the conditioning circuit, I'm going to paste this into here. Instead of getting the polarity, we don't need the polarity anymore. We do need the thruster, but the thruster is going to come from this value. Control X. Anyway, so this is the thruster index. I'm going to call it TI over here, the thruster index. And I is more the polarity I. Instead of this one equaling a new thruster, it's going to be thrusters TI. Okay, that's going to give us the down thruster. So I'm going to call this Y. All right, so the next one we need is going to be the Z. That's going to be the next one in order. So we're going to say var Z equals thrusters TI plus 2. And that leaves the last one, which is for X, to be right before that. So, oh, actually I could do it here. Var X equals thrusters TI plus 1. Okay, so now I don't need the rest of the information that's in there, but I have these variables. I will need to set the Y variable back. So let's also put this one in here. Thrusters TI equals Y. So we put Y back when we're done, but we're not going to make any change to X or Z. What we will do is we're now going to say that Y.power plus equals X to Y times X.power. And we're also going to say Y.power plus equals Z to Y times Z.power. I suppose rather than having two separate lines for this, what I could do is get rid of the plus equals and get rid of this stuff. So this is all one line, or at least logically expressed down to 2 lines. I'm going to do mathf.min. Okay, and the minimum is going to be 1f, comma, and we're going to wrap this. We do get that variable amount of power coming out of it, but we guarantee that it can't go over 100% power. And that's our conditioning circuit. X is supposed to be plus 2. Z is supposed to be plus 1. We did Z first. All right, again, checking here. Works as expected. Now Z to Y1, going back into here and drive forward. There we go. Check that out. Excellent. Now let's make another change. Let's go over to here and put this on X to Y as well. And let's also give ourselves a little bit more driving force. So 3,000. Sure. Back to the game. And let's come over to this side. Theoretically, I should start getting up onto the wall. There. Yeah, check that out. I'm now on the wall, switching to this side, surfing around. It's all very wobbly at the moment, but I can increase the angular damping to deal with that. So setting that to 5 ended up resolving the damping issue in a lot of the physics I was using. Hey, where's the, there we go. Let's try driving on the side of the wall now. Cool. why do I have the values for x to y and z to y separated out? This comes down to the whole reason that I created the conditioning circuit in the first place, is to try to condition it similar to how I might perceive a muscle car to drive in anti-gravity versus an exotic car. So when you think of something like a Lamborghini or a Lotus, when you turn at high speeds, you're expecting that car to turn like it's on rails. A muscle car, on the other hand, one of the big things you think about is the takeoff, that it has so much power that it literally lifts the front of the car off the ground. Now, when you're looking at that style of gameplay and you are transferring it into hover physics, a muscle car style would be able to ram straight into a wall and it would rise faster. So it's got that rise as it's getting up there, it'll push off the walls faster. And since the exotic cars tend to want to turn easier, a way to transfer that one over is by using the X to Y. So if we're hitting a wall on the side, we can convert over to that one and switch to walls as we're traveling around sideways. So we've got different ways of dealing with it. So let's start dealing with gravity. How do we get gravity to reorient itself so that when we drive up to a wall, we can actually stay on it? For instance, right now, if I were to select this wall and increase its size, let's actually make it pretty big. There. And then we start the game. I'm going to try driving up the wall. Oh, don't have enough pressure. We're going to go over to the car, change our forces over to drive force of 3,000. And now let's try driving back up it again. There. Now we're able to drive up the wall. However, it just starts drifting us right back down. We want to be able to stay on the wall. So let's go to our skateboard and we're going to need to get a gravity. Right now, we don't deal with gravity at all in this for the natural gravity of the world. We let RigidBody do the work. In fact, let's go back to RigidBody and turn off use gravity. So without that, our car will get pushed off the ground a little bit when it first starts and then just keep going. Oh, were we above the ground to begin with? Let's go forward. There. Now it just keeps going up and never comes back down. So that doesn't work very well. We're going to start taking control of our own gravity now. To do that, we're going to need a gravity normal and we're going to need a gravity force. So in our values here, let's go with public float gravity force equals 1,000. Public vector 3, gravity normal equals vector 3 dot down. Okay, so we're going to duplicate gravity from RigidBody for right now. So to do that, I'm going to go down to our physics code. And at the bottom of our physics code, we add this force. We add a force for our driving force. We add torque. And let's also add our gravity. So this dot RB, RigidBody, dot add force, gravity force, times delta time dot delta time. And the last one is the normal, gravity normal. All right, now with this in place, our car should drift back down again. Let's test it out. All right, so the initial gravity force is 1,000 and down is a y of -1. So we're ready to go. Drive force, I'm going to set that to 3,000. Also, I reduced these values earlier as kind of an example of areas to change in the game. I'm going to increase them. Let's go to 1 and 1. That'll make it far more responsive to turning an angle or turning a corner. This should operate the same way as before. So when I drive over here to the wall, I can now drive up the wall and then turn, and we see ourselves falling right back to Earth. Maybe a little bit faster. So our math isn't exactly the same. I mean, I guess you could have argued 981 probably would have been the proper gravity force to add. But we're not dealing with accuracy here. We're dealing with a game and we want to deal with the feel. And so the amount of gravity force that you put in beforehand and the amount of gravity counter force that you get from it, that changes the feel of it. So don't think of it in percentages. Think of it in actual numbers. So over here, we have our drive force, thrust force. So we have our thrust force at 1,000. Since we have control of the gravity now, we can alter this. So let's set this to 10 and this one to 10. So our gravity force and our thrust force have been significantly reduced. Let's go back into the game and play. All right, we can see that, look, it's stabilizing. It's still pushing up. It's getting farther from the ground. The distance is increasing and the power is reducing. So we had lower numbers, but we have much less of an effect. So if I go into the game, and I try driving, look at that, how slowly it pushes away from it. Gravity force, it should be times 4. So that should be 40, because there's 4 counter forces, 1 up force. But that doesn't really matter too much. The point is that this is not effective enough for us. I need those numbers to be considerably higher. So if I change the thrust force to 1,000, then it pushes up really fast. And now I need to increase this one to 1,000. And it drops it down really fast. And so by increasing these numbers, even if our percentage remains the same for how much power we're putting into this, it changes how quickly it can react and respond. Anyway, now let's see about driving up the wall. We drove up the wall and we sink back down to the ground right away. Let's adjust the gravity so the gravity sticks with us. All right, so we need to update what our gravity normal is. And how do we do that? One really easy way is we're going to add one additional check inside of here. And we can do this right after the end of all these other ones. That's fine. At this point, we're going to do another raycast. So let me grab the values I used for this before. I'll just paste that in here. Now, the origin is going to be transform.position, and the normal, negative gravity normal. So our gravity normal is a constant force that's being applied to the car. We're going to take the opposite direction of it and assume that that's the direction we want to go. So if gravity is pushing this way, oh, actually, no, that's this exact same. We want to go the same direction as the gravity force is exerting. And we're going to try to detect what's below us. Now, if we hit a surface on this, then the only thing we're going to do is change the gravity normal. Gravity normal equals hit.normal. Now, the hit.normal, if we hit a surface directly below us, we hit that surface, the normal is going to be the exact opposite. That's not what we want. So we do need the negative of this normal. Oh, I can't use hit, so we're going to call this g-hit. Oh. That's got it. It's not the gravity normal that I want to use in this one. My apologies. It's transform.down, which doesn't exist. So we're going to use transform.up, but we're going to use the negative of it. So we're taking whatever the car is over and making a point directly out of the bottom of the car. Now let's try this again. So here we go up the surface. I turn. Gravity isn't really fighting me that much anymore. The car came to a stop. I can now drive on the surface. In fact, I gain more abilities. I can now go over the edges. If I go too fast, that's a bit of a problem. I need to get back there because I'll just start drifting down. Actually, let's just do it that way. There. So if I go to the scene view and I pressed F, you can see the car's drifting that way, falling in the direction of its last known gravity. Just continues to go that direction. I could potentially regain a little bit of control by steering it, and now I got back to the ground. Effectively, that worked as I expected. How you handle it when it falls off, that's up to you. I mean, you could use like the Mario Brothers, the Mario Karts option, where once you get far enough away from the track, then it automatically has something grab you and pull you back onto the track and put. You could also have something where you have a boundary that if you get far enough away from the road or far enough away from a surface, that it pulls you back to the last point you were in contact with. I do want to give you a bit of information on this as to how it actually relates to car physics directly, not hover cars, but cars. For instance, what if I were to take my max distance and drop it down? Not negative, just a little bit above the ground. Then all of a sudden, this looks like a lot more like a car. I mean, we are just a little bit above the ground. What if I change that max distance just a little bit more? There, we're still above the ground. But it doesn't look like it. In fact, that offset of where we have this, we could take the actual car and drop the car down just a little bit. There. That looks like a car that's just sitting here. But when I go into the game, I now have a car that drives around. Now, this doesn't work exactly the same way as a car. For instance, I can turn while I'm sitting still. There's a lot more that can go into it than this, but a core operation to it is just detecting where the ground is from each one of the tires. And for those, you say, okay, give me a raycast from this tire down. We detect that distance. And now for most of the car physics, we have a suspension system. And that suspension system allows the car height and the tire height to be at different positions. They can vary while it's moving. And this is important. The physics of a car changes. How much pressure it's putting in, how much the car is allowed to destabilize from left to right changes the amount of pressure it's going to be able to apply or how quickly it'll balance it back out to the other side. I'm not going to turn this into a normal car physics, but I just want to give you the example of it. So let's say, for one thing, since I can spin in place, how would I solve this one? So if I go back to my code, here's where we add our force and we add our torque. When I am developing how much torque I can put in here, instead of just using move input X and saying that, okay, we can always apply this, I would also put in, what is our current drive force? How fast are we moving right now? And now we're doing this by add force. So I would actually say, instead of that, I would add times RB dot linear velocity times, not dot magnitude. So this gives me how much force it has to apply over to how it can drive. So if I'm moving, then I've got a linear velocity. Now, granted, I could be in a drift sideways. And so there's a lot of different numbers you could start bringing in here, but this is a good start. So, all right, assuming that we had our speed taken care of, let's jump over to one more thing in this. If I go to the car and I want to drift, I want to make a car that can drift more, then it's not that it's going to drift all the time, or maybe that is what we want, but we do want to control this so that it turns on more at particular times or gradually increases as your speed increases. Because most cars, they have they have traction and they have a certain amount that their tires can grip the road. Lotus Elise was particularly well known for this one. They had to change their tires to be tires that would slip faster because the tires worked so well. People would just be trusting these and they would turn. And then by the time that they hit a point of force where it started to slip, that was it. There was no recovery from that. You already hit the limit. And so they had to reduce the amount of traction on the tire to allow the car to start to slip sooner while the car could still maintain some grip. So in our case, we're going to duplicate this by going over to our RigidBody, and we're going to increase the linear dampening, and we're going to increase the drive force. Let's go times 4. And let's try driving. So it's not too far off of where we were, but this moves kind of like a car. It feels more like a car right now. Now let's turn on the drift. So I'm going to take the linear dampening and change this down to 2. Now keep in mind, I'm doing this all manually right now, or let's change it down to 1. Now as I drive forward, so drive and then turn. Drive, turn. You can see that it's moving past it. Think of how the experience changes, how the feel changes when you're driving. All right. I hope you found this useful. I will talk to you later.